I'm not the speaker. I'm just the introducer. So I'm Mark Donner. I'm an engineering director here in the New York office. I would like to, it's my distinct pleasure and honor to introduce Joe Halpern, who's the head of the CS department at Cornell. He started off as an honest mathematician and then fell into computer science, sort of the way many of the rest of us did over the course of years. He's done very many interesting things, including teaching mathematics in Ghana for 2 years. But I'll let him tell the rest of the story. He's going to talk tonight about Scrip systems, not script, Scrip. So funny money to you, or something on that order, but there's lots of them around, and I will let him tell the story. Joe.
Can you hear me back there? Okay. So the rules of the game are, do not wait to the end to ask questions. Ask them whenever you feel like asking them. If I think it's inappropriate or it makes more sense to wait to the end, I'm in charge. I'll tell you to wait, okay? So this is joint work with Ian Cash, who was my student. He's now at a competitor. He's at Microsoft in Cambridge, England. And Eric Friedman, who's now, although he was at Cornell. So as Mark said, Scrip is funny money. It's all over the place, actually. You can think of, as Mark pointed out, how did I get to the end? Scrip has been widely used. I'll explain the babysitting co-op story. That's coming up. It's used in systems like Karma and Brownie Points and Dandelion and Ant Farm. So these are all computer systems. So are the following: Agoric, Mariposa, Udals, Mirage Eggs. So here they've been used to prevent free riding. I'll explain that. And for resource allocation. So, but they're also used in the real world. Think of airline miles. They're Scrip, right? It's a way of keeping track of things, which you can use to get free trips and other things. In Ithaca, we have Ithaca hours, which is Scrip money that you can use to pay for some businesses. It can be very effective because you can think of Scrip as a market mechanism, and they can yield orderly systems beyond the ability of any individual to plan, implement, or understand. So this is saying basically the market is a good thing, but they're far from perfect. So we wanted to understand Scrip systems. Yeah. They're sort of on the border of Scrip and real money. So I mean, this isn't a talk on what is really Scrip, but I think to some extent they share some of the features of Scrip. So let me explain the Capitol Hill babysitting co-op story. This is a story that I read about in an article by Paul Krugman. Yes, Nobel Prize winning Paul Krugman. But there's a journal article, an econ journal, that his article was based on. So the story goes like this. A bunch of yuppies in Washington all had kids, and they decided they would form a babysitting co-op. They would babysit for each other. High tech. And so, of course, they didn't want to pay each other, but somehow they wanted to keep track of who was babysitting because they didn't want free riding. They didn't want it to be the case that, gee, people babysat for me 20 times and I never babysat for anybody else, right? So the way they did it is they had tokens. Tokens are Scrip. So everybody had some tokens, and if you wanted somebody to babysit for you, you had to give them a token. And you got a token when you babysat for someone else. So think of the Scrip as functioning like bookkeeping. It had no value in the outside world. It was just a system of tokens. Now, what was interesting is, at the beginning, the system worked terribly. Nobody was going out. Everybody was staying home. So, this is, we have this great system. How come nobody's going out? So these were Washington yuppies, right? So they legislated. You have to go out. It's good for you. Go out at least once a month. Get out of the house. Didn't work. Then they brought in a bright young economist, said, your problem is you haven't got enough tokens in the system. So they printed more tokens. Worked like a charm. People started going out. And they said, well, gee, if printing some tokens is good, it's got to be even better to print more tokens. They printed more tokens. Yes, Washington. The system crashed. Nobody went out anymore. Okay, time out. So think about, why did nobody go out at the beginning? And why did people stop going out when they printed more tokens? Any intuitions here? Everybody's afraid of running out. If you've only got 1 or 2 tokens, of course, if you have 0 tokens, you can't go out because if you don't have a token, you can't get somebody to babysit for you. That's the whole point. And if you only have 1 or 2, you might be worried, well, gee, what happens if my mom gets sick and I really need to go out, or, there's some special occasion. So it's clear if there are very few tokens in the system, people are afraid of going out because they're worried about running out of Scrip. Now what's the problem when they printed a whole bunch of Scrip? What went wrong then? Yeah. Yeah, so let's make precise why they don't have any. You're right. They don't have any value. Why don't they have any value? Let's some intuition. Sorry? There's a lot of them. They don't want to babysit anymore. They don't need anymore. That's exactly right. Right? In other words, if everybody has 20 tokens, say, why the hell do I need to go babysit for somebody else? 20 tokens. I mean, so there's no problem. I'm happy to go out. I got 20 tokens. But I don't have anybody who wants to babysit for me because everybody else has 20 tokens too, and they figure they don't need a 21st. Okay, so in our framework, and also in this story, which by the way was based on a real life situation, there really was a Washington babysitting co-op. There's no auctions, right? So it's not you can say, okay, I'll pay you 3 tokens to babysit. So we have to. So throughout this talk. I'll mention this again at the end because I think there's an interesting research question here. You have to assume that the price of a job is fixed. 1 token per job. No bargaining, no side payments. That's the market. Regardless, there's no inflation, no nothing. Although I'll talk about that too. Okay, so that's where we came in. We wanted to understand. And why do we want to understand? What was the research question to us as computer scientists? What's the right amount of money to pump into the system? What's the right amount of Scrip to pump into the system? If you say, well, too little is bad, too much is bad. Now, too little is bad because people don't have enough. They're worried they're going to run out. Too much is bad because everybody has too much. They don't want to babysit. Well, what's the sweet spot in the middle? We wanted to understand that. Okay, so that was our technical question. Are we all together? So now I'm going to have some technical slides, which I hope I can explain well, but you understand that's our motivation. That's what we want to do. Oh, sorry. Let's do this again. So our approach, we want to develop a microeconomic model. Think game theory. I'm coming at it from the point of view of game theory. I'll explain all of this. And I want to try to figure out what the optimal behavior is for agents in that model. What's the right thing to do? If you're rational and smart, understand how the system works, what should you do? I want to show that there's a stable outcome that's a Nash equilibrium. I'll explain what Nash equilibrium is. In fact, let me explain it now. So this is game theory. So how many people don't know what Nash equilibrium is? It's okay if you don't know. Okay, so let me explain. So have you heard of the movie A Beautiful Mind? John Nash, right? He got a Nobel Prize, right? This is what he got the prize for. It was his PhD thesis, by the way. So in game theory, the point is we have a bunch of strategic agents. They all have a strategy. Strategy is just what you're going to do in every situation. Now we're going to say a collection of strategies is an equilibrium, is a Nash equilibrium, if everybody is best responding given what everybody else is doing, that even if I know what all the rest of you are doing, I have no motivation to do anything else other than what I'm doing. So fix a strategy for everybody. We're going to say that set of strategies, that collection of strategies, is an equilibrium, or is a Nash equilibrium, if, even if you knew what everybody else was doing, you would have no temptation to switch, to change what you were doing. Okay? That's a Nash equilibrium. You have no, it's a stable situation because nobody wants to change what they're doing. It's not necessarily a good situation. You might be totally unhappy with the equilibrium you're in. But nevertheless, you can't do better by unilaterally changing to something else. Okay? So we're trying to understand, and Nash equilibrium isn't perfect. I mean, I could give a whole other talk on problems with Nash equilibrium and ways to get around it, but that's not this talk. It is the case that in many situations of interest, especially if people really understand the system, what they end up doing is playing a Nash equilibrium. So we wanted to understand Nash equilibria in this setting with Scrip systems. Okay, are we together? That's the goal. And we wanted to use the understanding to maybe tell system designers how to build better systems. Right? So here's the formal model. It's not as bad as it looks, so let me explain it intuitively. This is some of the math you're going to get, but I'll try to make it easy. So our picture is we've got a bunch of agents, N, And for the purposes of this slide, let me assume that all agents are the same, and I'll explain in what ways they're the same. So in each round, one agent is chosen randomly to make a request. What I mean by make a request, you need babysitting. So I'm going to assume that the need for babysitting comes from the outside. It's not something you're planning strategically. You wake up one morning, you read in the paper, great movie playing, I want to go out, right? So I want babysitting tonight. So nature chooses somebody at random to need something, to want babysitting. So think in terms of babysitting. Now, in our general model, we assume that there are different types of players. So some players, if you like, are needier than others. So if you like, what this is assuming is everybody's equally likely to want babysitting, right? But you can imagine some people tend to want babysitting more than others. They like going out. That's okay. We allow that in the general model. But for this talk, let me not assume that. Now, the one strategic choice you have is if I say, look, I need some babysitting, who's willing to babysit for me tonight? Raise your hands. That's a strategic choice. You might decide I'm not interested in babysitting, right? Why might you say I'm not interested? It's because I have 20 tokens. I don't really want a 21st, okay? So you have to decide whether or not you want to babysit. Well, once you've decided, out of all the people who raised their hands and said, I'm willing to babysit, I'm going to choose one at random. Now, again, in our general model, we assume that the choice isn't necessarily totally random. You imagine that some people advertise better than others. So if you've got good advertising, you're more likely to be chosen than somebody who allows the advertiser or their reputation effects. But for the purposes of this talk, just to simplify things, let's assume you're chosen at random. Everybody's equally likely to get chosen. Now, the rest of it is the obvious thing. When the person who makes the request gives one token to the other person, so he pays, think of a token as being $1, but it's funny money, it's scrip. And you get 1 unit of utility. Utility, think of it as a measure of happiness. Okay? So the person who gets the babysitting done gets 1 unit of utility, and the person who does the babysitting and pays $1. So dollars and utilities are not the same. The tokens are just bookkeeping. What you really care about is happiness, right? So you get 1 unit of happiness if you get babysitting done for you. You lose alpha units of happiness if you do babysitting, and we're going to assume that alpha is a lot less than 1. Otherwise, the system would never get off the ground. If the amount of unhappiness you incurred by babysitting was more than the amount of happiness you were going to get by having somebody babysit for you, of course you'd never babysit, right? Because all you're getting is a token, and the token buys you babysitting in the future, right? So babysitting isn't worth the pain of doing babysitting. You'd never do it, right? So we're going to assume that you get 1 unit of happiness if you babysit, and you lose alpha units of happiness doing the babysitting, but alpha is a lot less than 1. Everybody else breaks even, and of course the person who asks to have the babysitting done has to pay $1 to the person who does the babysitting. But the $1 has nothing to do with happiness. Think of it as simply bookkeeping. It's a token. Okay? And the other thing we're going to assume is that there's what's called discounting. So a unit of happiness tomorrow is not as good as a unit of happiness today, right? So I'll pay you back on Tuesday for the $1 you're giving me today. The $1 is actually worth less on Tuesday than it's worth today. So we're assuming so technically we have a discount factor delta. Think of delta as being less than 1 but close to 1. So $1 today is worth delta dollars tomorrow. So think of delta as 0.9. Delta squared the next day, delta cubed the day after that, delta fourth the day after that. Question? So I'm told to repeat question, and the question is, why do I assume a delta at all? So if you don't want to assume that, think of, and we're going to think of this in the talk, think of delta as being very, very close to 1. But in fact, it seems that in real life, people do assume there's a delta less than 1. People act as if there's a delta less than 1. That getting something today is better than getting the same thing tomorrow. So people act. So this seems to be a real psychological phenomenon. It's not like we made it up. Now, in fact, for our results, we need to assume that n is relatively large, although it turns out like 100 is good enough as a practical matter, and delta is pretty close to 1. Okay? Yeah. So the question is this independent of a termination effect? So in this world, there's no termination. People live forever. Stay tuned. I mean, you'll see what the results are saying. So what I care about, think of me as a system designer. This is the total utility for an agent. So this is saying For each round R, look at how much utility you get in round R, which is either 0 or 1 or negative alpha. Those are the only possible utility quantities, right? If you get babysitting done for you in round R, then UIR is 1. If you do babysitting for somebody else around R, UIR is negative alpha. And if you don't babysit or get babysitting done, this is 0. And the delta of the R just says, something 10 rounds out, you multiply by delta to the 10th, right? So this is your total utility. For me, the system designer, what I care about is maximizing social welfare, which is the social welfare is just going to be the sum of everybody's utility. I want everybody to be as happy as possible, right? I want to design a system where I'm going to have very high total utility. Are we together? Right? So I just add everybody's utility. Here I'm weighting everybody the same way. And of course, I'm going to maximize total utility, just to sort of keep this in the back of your mind, by making sure that whenever somebody wants babysitting done, they'll have a token to pay for it, and they'll have somebody who's willing to do babysitting. So again, think of the Washington babysitting co-op story. So there are two things that can go wrong. If there are very few tokens, if you've got a system of 10,000 people and you have 100 tokens, then it's clear that most people most of the time don't have a token. Bad. Bad for the point of view of a system designer who wants to maximize social welfare, because if you don't have very many tokens, even if you have 10,000 people and 20,000 tokens, there's a non-trivial chance somebody won't have a token, right? Just if you look at fluctuations, right? So I want a job done, I don't have a token, I'm unhappy. I could have been happier if I had a token to pay for it, right? Conversely, if I want a job done and there's lots of tokens floating around, nobody's going to, intuitively, I haven't said why yet, but nobody's going to volunteer. I'm also unhappy. I have lots of money to pay for you, but, nobody's raising their hand, right? So I want to maximize two probability, and that's what's, as you'll see later, what's going to happen is too few tokens in the system will be bad for social welfare, because a lot of times when somebody wants a job done, they won't have a token to pay for it. Too many tokens in the system will be bad for social welfare, because a lot of times when somebody wants a job done, nobody will raise their hand. Question? Sorry? Okay, so again, I'll repeat. So the question was, they could start asking for 5 tokens for babysitting rather than 1. I'm not allowing that. So in this system, prices are fixed. Now again, it's very interesting to ask what happens if you allow markets, where you can say, look, how much are you willing to bid for this job? I won't do it for 1, but maybe I'll do it for 3, right? So we're not allowing that. Again, I claim this is quite realistic. There are many markets in the world where prices are fixed. Certainly, I go, in Ithaca, where I live, they have Ithaca hours. They're fixed prices for things they're posted. Think of all the things that you're aware of in the world where there are fixed posted prices. Now, I understand there's other situations where there's bargaining, but bargaining incurs overhead, right? So it's customers and producers like it much better when there are fixed prices. Again, as an empirical statement, there is. So again, look, this is Google. Google works by bids, right? And market design. I understand that. And it's very interesting to ask how things would change in this framework if we allowed bidding. But let me at least claim there are lots of real-world scenarios where there are fixed posted prices. So it's not like we're making up something that never happens in the real world. And let me, as a technical matter, what I'm about to tell you in this talk says nothing about what happens when there's sort of auctions for goods, although I'll come back to that at the end. Questions? Yep. You have to. So the question was, are my results robust under a no-trade negative utility penalty? Except I don't understand what that is. Well, the utilities are just what I have there. So your utility is either 0, negative alpha, or 1 in each round, and there's nothing hidden. That's the utility. Yeah. Yeah. So think of social welfare as overall happiness, which is literally defined as the sum of everybody's utility. So this is the utility for a particular agent I. So 10,000 agents, each one has their utility. Just add them all up. That's social welfare by definition. Mario. So the question is this situation going to result in a situation where a few people do all the work? In practice, in fact, not just in practice, we can prove theoretically no. Things will be quite uniform. But stay tuned. Let me get to technical results. So I think at this point, I will stop questions and keep going. So our assumption, so let me repeat, I was saying this before, for ease of exposition, just, and this is not what we assume in the full paper, I've assumed that agents are homogeneous in the following sense. They have the same cost alpha for performing work. Now, of course, in the real world, that might be true, but in many cases, it might not. So I might love babysitting your kids. My cost for babysitting your kids is very low, or I might hate babysitting your kids. They're real brats, and the cost will be high. So there's no reason to assume that all agents feel. Some people love babysitting, some people hate it. I've assumed that everybody has the same probability of being chosen if they volunteer, right? So among the people who raise their hands, I choose at random, so everybody's equally likely. I don't have to assume that. I've assumed that everybody gets the same utility for having a job done. Of course, in the real world, I might love going out to a movie. You might sort of, movies are good, but, I mean, I don't mind staying at home and reading. I've assumed that everybody uses the same discount factor. Think of discount factor as measuring your patience. So roughly speaking, it's saying, how patient are you? If you get $1 today, but you're not going to be able to use it for 3 weeks, are you okay with that? If you have it, so your discount factor is between 0 and 1, I'm going to assume that people are pretty patient. Discount factor is close to 1. But a discount factor that's close to 0 is saying, hey, if I don't get to spend my money right away, think of like my kids when they were young, it's not good for anything, right? So if I can't spend the next, money 2 days from now is basically worthless, right? So that's, if you think of a discount factor like a quarter, so $1 today is worth like a 16th of a dollar tomorrow and a 64th of a dollar 3 days from now, pretty close to 0. So if you're very impatient, your discount factor is close to 0. If you're very patient, your discount factor is very close to 1. Are we together? That's the technical content. So again, I'm assuming that everybody has the same discount factor. That might not be true. And in our general model, we have what economists call different types of agent, where a type is characterized by their alpha, the probability of being chosen. Just all these 5 factors, we have a number for each of them, and that tuple of 5 numbers characterizes an agent. And again, let me repeat, I've said it 3 times, I think. The price of a job is fixed. So there's been other work, some of it based on our work. So Hens et al. Did their work independently. They were economists. A slightly different model. They assumed that there was no cost for volunteering. That is, babysitting is, no pain at all. But they assumed that agents' utilities change over time. We don't. And they assume that agents choose whether to provide service, request service, or opt out. They have a slightly different model, but again, they're investigating Scrip systems. Aprayas and Johari actually had a paper that followed on to ours, but their focus was on finding equilibrium prices, which ours isn't, but I'm being a good scholar and telling you about other work. So back to what we were doing. We're interested in what seems to me the most natural kind of strategy, which is that you have a threshold. And the way you think about the threshold, so suppose my threshold is $7. Why should I work? Under what circumstances will I work? What's the intuition? So again, let me ask you to make sure that we're all on the same page here. What would induce you to raise your hand if somebody says, I need a babysitter? Yeah. Sorry? You have something coming up. Well, in this model, you don't, because remember, you're chosen at random. But you can figure out the probability that you'll have something coming up. But why might one person be more likely to raise their hand than another? Yeah. Yeah, less tokens, right? So basically, the intuition is, if you have very few tokens, you're nervous. Why are you nervous? So suppose you have 2 tokens. You're nervous that you might want something 3 times in a row before you get a chance to, raising your hand doesn't guarantee that you're going to get work, right? Raising your hand just says, I'm one of the 25 people who raised their hand. I probably 1 over 25 of being chosen, right? So intuitively, you volunteer for a job if you feel like you're running low, whatever that means. And that's what we're going to be talking about. At what point do I start getting nervous? When do I start feeling like I'm running low? And if you feel like you have a lot of money, you don't raise your hand. So if that's the way you're thinking, you're following a threshold strategy. So a threshold strategy says, I have a threshold, let's say, of $7. And what that means is if I have less, or 7 tokens, if I have less than 7 tokens, I volunteer. If I have 7 or more, I don't. Are we together? That seems like the most natural strategy. You have some fixed threshold, very easy to implement, obviously, in a computer system. You have some fixed threshold that says, below that, I raise my hand, above that, I don't. Okay? That's the threshold strategy. Oh, I did it again. 2 buttons aside, better human factors. So, why do I want to satisfy stuff? And why don't I? This is just an argument for threshold. If I have lots of money, I don't raise my hand. If I'm running short, I do raise my hand, right? Yeah. Right. So again, so the question is, do all the agents have prior independent alphas? And the answer is they all have the same alpha, right? In the general model, they don't. So in the general model, part of your type or personality is your alpha, and we allow for finitely many types. It could be a very large number of agents, but there might be 7 types of agents. So your type is characterized by 5 numbers. One of them is the alpha. And sorry, your second question was, what about auctions? So the question is, do they have insight into the success of prior auctions? In a precise sense, as we'll see, they don't have to. Okay, so the answer is it's irrelevant, but let me make that precise. Okay, so everybody understands the threshold strategy. You understand what's sort of the obvious thing to do. So threshold strategy, let me call it SK, is volunteer if I have less than K dollars. So think of K as your comfort level. And so the question we're asking technically is it reasonable? Not my phone, your phone. So I feel like the airline pilot that says, everybody should turn off their cell phones, right? So is it reasonable to play a threshold strategy, and how does the system behave if everyone plays a threshold strategy? The way we're going to formalize that, we're going to prove that there's a Nash equilibrium where everybody plays a threshold strategy. Actually, there's an easy Nash equilibrium where everybody plays a threshold strategy. That's where everybody plays the threshold strategy of 0. A threshold strategy of 0 says you never volunteer, because you volunteer if you have less than $0, and you'll never have less than $0, right? So that's a threshold strategy where K is 0. That's a special case where K is 0. And I claim if everybody plays the strategy S0, which is never volunteer, that's an equilibrium. Why is it an equilibrium? Well, I claim if none of you are ever going to volunteer, the best thing for me to do is not to volunteer. Why should I volunteer? Well, if I volunteer, you will happily, so you need babysitting. If I say, okay, yes, I'm willing to do it, you say, great, I'll take you. Babysit, here's a token. Okay, now you have a token. What can you do with the token? Well, next time you want babysitting, you say, oh, who wants to volunteer? But all the rest of you are never volunteering. What good is my token doing? Okay? So clearly, if everybody else is following the strategy of never volunteer, my best response is never volunteer. So there is a Nash equilibrium where nobody ever volunteers. That's obviously not very interesting. So we're interested in the question of, is there a non-trivial equilibrium, a threshold K where everybody plays K and they're happy with that and K is not 0, right? And how does it behave? And you'll see it does very interesting things. So you had asked, do you know what other people are doing in this successive? Let me sort of start addressing that question. So here's some technical stuff, so bear with me a few seconds. I think I can explain this, and there isn't that much of it anyway, but I think it's sort of cool. So out of curiosity, how many people have heard of maximum entropy? Even if you don't know what it is, how many people have at least heard of it? Fair number of you, okay. So it turns out that I'll explain it. I don't assume you know it. The maximum entropy characterizes the distribution of money in the system. And knowing that, we can use that to prove that there is not technically a Nash equilibrium, but an epsilon Nash equilibrium. So a Nash equilibrium says, given what everybody else is doing, what I'm doing is a best response. Epsilon says, what I'm doing is a best response to within a very small epsilon. Like there might be something I could do that's better, but it can't be more. Think of epsilon as being like 0.001. It's not going to be more than epsilon better. So if I don't want to spend hours thinking about what's the best thing to do, I'm happy with just playing my threshold strategy. Well, maybe out there's something a bit better, but it's not going to be a lot better. You can make epsilon as small as you want, as it happens. So I mentioned that is also a Nash equilibrium if everybody plays a threshold of 0, never volunteering, but it's not interesting. Now, here's the interesting thing for system designers. What we're going to show is, so no matter how much money there is in the system, there is an equilibrium. But now it turns out as you pump more and more money into the system, start at 0, pump more money into the system, social welfare improves. Right? So if you're a system designer, you want to pump more and more money into the system up until a certain critical point. So again, going back to the Washington babysitting co-op story, you can see that if you start with $0, that means nobody can ever do any babysitting because they have no tokens. Putting more money into the system, that increases social welfare. People are going to be happier. They're going to be able to pay for babysitting. Until you get to a certain point where there's lots of money floating around the system and nobody's going to want to volunteer, right? That's the intuition. But what we show is it's a critical point. So things get better and better and better and better till there's a crash. And it's a sharp crash. It's like you fall off a cliff. So if you're a system designer, there's sort of a magic amount of money. All that matters, it turns out, is the average amount of money per person. So there's a particular number like 7. If you're a system designer, independent of the number of people in the system, you want to have an average of $7 per person in the system. You want to get as close to that as you can. But if you have a little bit more than that, so putting in more and more money up till you get to 7 makes things better and better and better. The total amount of happiness in the system keeps increasing up until you get to this cliff point, and then you fall off the cliff, and then nobody's ever going to volunteer anymore, and people are extremely unhappy. No babysitting gets done at all, right? So now this assumes, of course, that everybody's totally rational. Now, of course, in the real world, even if you totally understand the system, not everybody's rational. So if I were a system designer, I wouldn't push my luck and go all the way to 7 or even 6.999. You want to back off a bit, and I'll talk about that later in the talk. But this is the lesson for system designers, that there is a magic number, which is the average amount of money per person, and that's what you want to hit. Well, you don't exactly want to hit it. You probably in the real world want to get fairly close, but you don't want to push your luck, right? But if you go over it, the system will crash. Very bad. Crash in the sense of nobody will ever volunteer. Are we together? So that's what the mathematics is telling you. They've actually observed this phenomenon in the real world. I think in Second Life, actually. If somebody knows more about this, I mean, somebody mentioned this to me after talk. It actually observed. Second Life is a game, right? And apparently this phenomenon has been observed. So we can sort of simulate it, but it happens. Okay, next few slides are technical. Bear with me. If you're totally non-mathematical, it's probably maybe a time to tune out. But I will try to make it as accessible as possible, and then we'll get back to what we learned from this. Okay? So formally, we can view the system as what's called a Markov chain. A Markov chain. Well, okay, how many people have heard of Markov chains? A fair number of you. Okay, but even I'll try to make sense of this. So a Markov chain consists of a collection of states and transitions between states. So if you're in this state, you'll move to another state with a certain probability. So think of it as what we call a graph, so a bunch of nodes. The nodes are the states. The states are connected by edges, and the edges have probabilities on them. And the way to think about this, if you're at this node, you look at where the edges are going. Each edge is labeled with a number. That's a probability. The sum of the numbers is 1. And says, with probably a third, you're going here. With probably a quarter, you're going here. And with probability whatever's left, 5/12, you're going over here. Okay, so each of the edges is labeled with a number that's a probability. That's a Markov chain. So it'll tell you, it doesn't tell you exactly what's going to happen. You can sort of figure out how likely is each path, right? If I'm here, I'm going to go here, then I'm going to go here. What's the probability of doing this, right? That's a Markov chain. And you can, so what are the states? The states are just a tuple that describes how much money each agent has. So imagine I've got 1,000 agents and I've got $2,000 in the system, 2,000 tokens. A state just describes how those 2,000 tokens are split up between the agents. You've got 3, you've got 2, you've got 27. You're sitting there with 300 of them. A bunch of people have zeros. Okay, that's a state. Who has how much money? Are we together? Now, if you're in a certain state, what's the probability of moving to another state? Well, the only other state I can move to, if I'm talking about tokens, is one person gets one more token and somebody else gets one less token. That's the only move that I'm allowed, right? So if you have 300 and you need babysitting done and you volunteered, then one of your 300 is going over to him. You have 299 and you have whatever you had plus 1. Are we together? Those are the state transitions, but there are lots of possible transitions because somebody is chosen at random. So everybody is equally likely to be chosen to want babysitting. Now, I can't tell you what the transition function is until I tell you what strategy everybody's following. So suppose we fix everybody else at following a threshold of 7, let's say. Once I fix everybody else at following a threshold of 7, then I can describe this as a Markov chain. Because I can say, look, with equal likelihood, each one of you is going to be chosen to want something. We're in a particular state. Remember, state is a tuple saying how much money everybody has. Okay, so if there's 200 of you here with probably 1 over 200, Mark has chosen to want something. If he has greater than $0, he can say, okay, who's willing to do a job? If he has 0, that's it. He's chosen, but nothing happens. So it's probably 1 we stay in the same state if he's chosen. But otherwise, everybody who has less than $7 will volunteer because we all have a threshold of 7. So everybody with fewer than $7 will volunteer. And one of them is chosen at random to do the job. And Mark's money goes down by $1, and whoever's chosen to do the job, their money goes up by $1. That's the transition. So it's easy once we know everybody else's strategy, everybody else's threshold, to compute the transitions. Is that clear? I mean, even if you don't understand, there's no deep math going on. That's the Markov chain, right? Now, a key fact about this Markov chain is if you run it for a while, you just keep doing, nature chooses somebody at random, you see what happens. What's going to happen after a while, and this is just, there's books and books on Markov theory, so I'll explain why this happens. You're going to end up in a situation where each state is equally likely. This is a standard, like Theorem 2 in any standard book of Markov chains. I'm not going to prove it, but the key observation is that the transitions are symmetrical. What I mean by that, and that I will explain, is that the probability of going from state 1 to state 2 is exactly the same as the probability of coming back from state 2 to state 1. And I'll explain why in a second. So then we'll open up your favorite book on Markov chains, and there's lots. And one of the theorems says, in any situation where the probabilities are symmetric, after a while you end up in a situation where all states are equally likely. So let me explain the symmetry. So again, symmetry means that the probability of going from state 1 to state 2 is exactly the same as the probability of coming back from 2 to 1. Well, what's the probability of going from state 1 to state 2? Remember, the only states I'm interested in is ones where the transition means I have $1 less, and let's say Stu has $1 more. Those are the only possible transitions, right? So let's look at a situation where I'm the one who wanted babysitting done. So that happened with probably 1 over n that I was chosen. And let's look at all the people. Again, I fixed the threshold, let's say it's 7. So let's fix all the people who have $7 or less, have less than $7. They're going to volunteer. And Stewart is one of them. And each one is equally likely to get chosen. So the probability of making that transition is 1 over n times 1 over m, where m is the number of volunteers. What's the probability of coming back? Well, it's the probability that Stewart is chosen to want babysitting, which is 1 over n, and the probability that I get chosen, that I volunteer and I get chosen. But in the long run, if the threshold that everybody's playing is k, after a while, nobody will ever have more than k dollars. Because if you had more than k, you're going to come down to k. You'll never volunteer until you're at k or below, and you'll never go above k. So after the system's in place, do you see that? So if the threshold is 7, you might start out life. I don't care how you start out life. You might not start out with $50. But if everybody is playing a threshold of 7, well, you'll have 50, then you'll want something done, you'll want 49, 40. You'll never volunteer till you're below 7. And once you're below 7, you'll never rise above it. So after some initial period, I don't care what state we started out in, we'll be in a situation where nobody has more than 7, right? So let me talk about again why the probability is 1 over m coming back. So again, the probability of me wanting something is 1 over n, and Stewart being chosen is 1 over m. That means that m people had $7 or less. Had less than $7. Well, coming back is the probability of Stewart being chosen. That's 1 over n. And what's the probability that there's going to be a volunteer? Well, there's 1 fewer volunteer, Stewart, but there's 1 more volunteer, that's me, and I will have less than m dollars because even if I had m before, I gave Stewart $1, so I have less than m. So it's the same 1 over n times 1. There's exactly the same volunteers when I wanted a job done as when Stewart wants a job done, except that before Stewart volunteered and I didn't, because you don't volunteer for yourself, and now I'm volunteering and Stewart is. So it's trivial. And as I say, there's this theorem, which I'm not going to prove, that says if you have that situation, all states are equally likely. Seems good. We understand the system, right? There's one slight problem. Oh, God, I did it again. You can see I'm a high-tech kind of guy. So I don't care about exactly how much money Stewart has and exactly how much money Mark has and exactly how much money Maliam has. I really care about the distribution of money. What fraction of people, what I really care about is what fraction of people have less than K dollars. Why do I care what fraction of people have less than K dollars? Why should I care about that? Sorry? Let's get a more practical answer. Why do I care about the number of people who have less than K dollars? It tells me the number of volunteers. And why do I care about that? Yeah. So look, I'm trying to figure out. So suppose all the rest of you are following threshold strategy K. I'm trying to figure out what I should do. I'm noise. I'm not going to affect anything. So I'm trying to figure out my best response. All the rest of you are clamped at following a threshold strategy of 7. Are we together? And I'm trying to figure out what I should do in response. Well, what should I be comfortable with? Should I set my threshold at 10? Should I set my threshold at 3? What's the right number? Well, what I want to know is, what's my competition if I volunteer? I mean, what I need to figure out, here I'm sitting there with 10 tokens. And is that a good number or not? Should I feel comfortable having 10 tokens? Well, what do I need to know to figure it out? Well, what I need to know is, how likely am I to run out of tokens before I can replenish, right? If I'm worried that I'm going to run out of tokens before I can, in other words, I'm worried that I'm going to be chosen to want something 11 times before I get a chance to volunteer and be chosen. Are we together? Because then I'll be unhappy, right? Of course, it's always possible that I get chosen 11 times in a row. I mean, this is random. It could be coin lands heads, 11 times in a row. But I have to figure out how likely that is, right? So what I have to figure out, are we together, is the probability that I'll be chosen 11 times before I get a chance to make a token, right? That's what I'm interested in. But now I claim, so I need to know what my competition is going to be like when I volunteer. Now, if all the rest of you are following a threshold strategy of 7, my competition is exactly the number of people who have less than $7. Does that make sense? That's why I want to understand. So I don't care whether it's Stuart who volunteers, or David who volunteers, or Mark who volunteers. I don't care who volunteers. I just want to know how many of you volunteer, right? The names of the people who volunteer is totally irrelevant. So I don't want to know who has $5 and who has $3. I want to know what fraction of people have $5 and $3 and $6. Well, actually, all I really care about is what fraction of people have less than $7. Are we together? That's the technical point here. You got that? You're in good shape. So now look at what happens. Suppose we have n agents. Suppose I tell you there are $2 in the system. Well, what could happen? It could be you're the agents. One person has the $2. How many ways are there for that to happen? Do you remember your combinatorics from high school? If you have n agents, how many ways are there that one of them has $2? Not very hard. N ways, right? Okay. The other possibility is those $2, one person has, two different people each have $1. Right? So I'm thinking, how could the $2 be spread around the system? Well, either one person has both dollars, or two different people each have $1. How many ways are there for two different people to have $1? Remember this from high school? N choose 2, n times n minus 1 over 2. So n choose 2, that's how you choose 2 people out of n to have $1, is about n squared. It's n squared over 2, or n times n minus 1 over 2. So there's n ways that one person has $2, n choose 2 ways that 2 people each have $1. N choose 2 is much bigger than n. N squared is much bigger than n for large values of n. So it's far more likely that if I have $2 in the system, that each of 2 people will each have $1, than that one person has $2. Now that generalizes. And in fact, this is an instance of what physicists call the concentration phenomenon. And okay, here's the math. Actually, I'll skip the math because I'm getting close to 7:30. But so what maximum entropy does, so okay, let me say a little bit. Given a distribution mu, so think of mu of I as being the number of agents that have $I, the fraction of agents that have $I. So there's n of you. If, suppose n is 200, if 18 of you have $3, that means 9% of you have $3. So mu of 3 would be 0.09, 9 over 100, right? So mu of I is the fraction of agents with $I. Now the entropy of the function of the distribution mu, this is the entropy function, is mu of I log mu of I. So it's the fraction of agents that have $3 times log of the fraction of agents that have $3 and sum that up, put a minus sign in front. That's the entropy of a distribution. For those of you who are familiar with it, that's what it is. If not, don't worry about it. But it turns out that this is the key mathematical fact, that the number of agents, there are lots of different ways to distribute N dollars among, to distribute capital N dollars, like $10,000 among 500 people. Lots of, one person could have 5,000, one person could have 0, right? There's lots of different ways of doing it. But it turns out that ways that end up having a distribution of money that's very close to the entropy distribution, maximum entropy distribution, dominate all other ways. So that the number of ways is characterized, the likelihood of having the distribution of money be characterized by probability mu is characterized by the entropy of mu. The distribution with the greatest entropy or distributions close to that are far, far more likely than anything else. What does that mean in practice? This is an answer to your question about why I don't have to know anything about previous auctions. I know if N is reasonably large. Yes. So as long as I know how much money is in circulation, if N is reasonably large, then I know almost for sure, like with probability, in 9,999 circumstances out of 10,000, very, very close to 1, I know for sure what fraction of agents have $0, what fraction of agents have $1, what fraction of agents have $2. Well, within a very small fudge factor of epsilon. It's characterized by the distribution that maximizes entropy, that maximizes this expression. This expression of this. The entropy expression. It's the distribution that maximizes the entropy is the one that almost surely characterizes the fraction of agents that have each varying amount of money. So I don't have to know anything else. I know what my competition is going to be like. I know how many people are going to, if the threshold is 7, I know almost for sure, like I would bet huge sums of money on it. You're much safer betting on this than crossing the street. That's how sure you are. How many agents are going to volunteer in each round? I don't know who they are. So I don't know which agents have $3, which ones have $5, but I know what fraction of agents will have $3, what fraction will have $5, and in particular, if the threshold is 7, what fraction will have less than $7. So I know what my competition is going to be like. I know every time I raise my hand, almost for sure, how many other people are going to raise their hands. Each round is going to be 112 people raising their hand, almost for sure. Different people. Are we together? That's sort of the power of mathematics here. So I can now figure out, it's a fairly straightforward computation, what my threshold ought to be. It's the point where the likelihood of, the cost of not raising my hand exceeds the cost of raising my hand. In other words, I'm worried, how likely is it that I'm going to run out of money if I have 10 tokens? How likely will I run out? Knowing what my competition is like, I can figure out how likely I am to be chosen every time I raise my hand. I can figure out how many times it's going to be before I run out of money with all probability because I have the complete probabilistic model. I can figure out what's the right amount of tokens I should have if I'm going to do a best response. Okay, that's what this tells me. Now, here's a sanity check, even if you don't understand any of the mathematics. So what I've done now is I said clamp everybody at following a threshold of 7. Now suppose I change that and said clamp everybody at following a threshold of 10. Should my threshold go up or down? What's your intuition? So if I know all the rest of you are following a threshold of 10 compared to 7, so I figured out my best response. Let's say my best response, if you're following the threshold of 7, the right thing for me to do is to have 10 tokens, right? Suppose I raised your threshold to 10. So you're gonna raise your hand as long as you have 10 tokens or less. Should I raise my threshold or lower my threshold, or no clue, or any intuitions? Raise. Why? Okay, let's make it a bit more precise. I mean, you're sort of right. So that's the right answer. If other people are raising their threshold, I should raise my threshold, but why? There's a really good intuitive answer. Anybody else? Yeah. You'll have more competitors. That was exactly the right answer, right? If everybody else is raising their hand Before, they were all raising their hand if they had less than $7. Now they're raising their hand if they have less than $10. You have to be a little bit careful, because if the threshold is 10, the distribution changes, because before they only had amounts between 0 and 7. Now they have amounts between 0 and 10. So there's a slight subtlety here. But nevertheless, it's the case, and it's not hard to show, that if everybody's raising their threshold to 10, you're going to have more competition than when the threshold was 7. So you ought to raise your threshold. So the best response function, your best response function is a function of what everybody else's threshold is increasing. Yeah. No, it's not raising their price. It's raising when they're willing to volunteer. Raise their threshold. It's not a price, right? The price is always 1 token. There's no change in price. So it's raising your comfort level. Before you were willing to, you're only going to volunteer if you had fewer than 7 tokens. Now you're going to volunteer if you have fewer than 10 tokens. Does that help? Yeah, but you shouldn't. I mean, let's just stick to thinking about tokens and not price. So using this, what happens is there's a theorem for the technically oriented. There's a theorem by a famous mathematician named Alfred Tarski that more or less says if you have a monotonic function, so the best response function, which is what should I do given what you're doing? So you is everybody else. So if I know everybody else's best response is 7, what's my best response? If I know everybody else is clamped at 10, what's my best response? If everybody's clamped at 15, what's my best response? That best response function is monotonic. As I raise what everybody else's threshold is, my threshold, my best response goes up. If you have a monotonic function, there's a fixed point. A fixed point means everybody else is doing 12, my best response is 12. That's an equilibrium. In other words, if everybody's playing 12, they're best responding to everybody else playing 12. So even if I know that all the rest of you are playing 12, as 12 is a fixed point, then I'm playing the best response. That's a Nash equilibrium. So this theorem basically says that there's, as long as delta is close to 1 and there's enough agents, enough turns out to be like 100, then this is basically saying that there's an epsilon best reply that's a threshold strategy, and the best reply function is monotonic, and from that we can conclude that there's a greatest and least fixed point, and we can find the fixed point by iterating best response. Let me skip over this, and let me jump to the punchline that we have a Nash equilibrium and threshold strategies. But this is what I was saying before. How much money, suppose you know that. So you know, no matter, you're the system designer, no matter how much money you pump into the system, there's a threshold. That's good. There's a magic number like 12 that the agents can actually learn by just playing and discovering, just best responding to each other. They can figure out what the best response is. So there is a Nash equilibrium. We're all going to play 12. We're all going to happily play 12. And it's non-trivial one. Again, it's Nash equilibrium if we all play threshold of 0. That's not interesting. But there's a non-trivial Nash equilibrium. But that hasn't answered the question that, what's the right amount of money to pump into the system? And there, the key is, this is the three, we did experiments. We can actually both prove this mathematically and observe it by simulation. That as you pump more and more money into the system, you look at the total happiness of the system. Remember, you're totally happy. You increase happiness by making sure that when somebody wants a job done, they have money. Following this threshold strategy, they're unlikely to run out of money. Again, it's always possible to run out. You're using a threshold of 10. It's always possible that 10 times in a row, very quickly, you'll want a job done before you get a chance to make an extra dollar. It's possible, but unlikely. As you pump more money into the system, that likelihood goes down. But then you want to worry that will it be the case that people will volunteer? And so there's a magic threshold where people all of a sudden stop volunteering. And that was a surprise. There was a cliff. That it happens all of a sudden that you reach this magic number and people stop volunteering. And this says something. So now let me talk about system design issues. I'll try to finish up in the next 5 minutes or so. Yeah. No, so we're looking at, we're not clamping the threshold. We're looking at what's the equilibrium. And the equilibrium will change as you pump money into the system. Right, so I'm not setting the threshold. Now I'm assuming everybody's a rational agent. They're all going to play a Nash Equilibrium. So if I, in other words, if I set everybody at 7, then you might think, well, gee, why should I play 7? 12 is better for me, right? So you want that, the equilibrium is everybody's playing 12, and that's also the best response. 12 is the best response to everybody playing 12. Am I making sense? So look, I'm not so happy. So let me say, okay. So what I'm claiming is there's a unique, technically greatest fixed point. So once you fix the money supply, there is a magic number that you can compute, and I can even give you the procedure, but let me not do that now. That gives you a fixed point. That is, there's a magic threshold. Let me say 12, but it's not 12. But it is a function of the money supply and the number of agents. What really matters, it turns out, is not the money supply and the number of agents separately. It's the average amount of money per person, right? So it's the money supply divided by the number of agents. That turns out to be the key parameter and the only parameter that matters. But once you fix that, so for every average amount of money per person, once you fix that, there's a magic threshold, let me say 12, but it's not, such that that's the greatest fixed point. So it's everybody playing 12 is the best response to everybody else playing 12. And there might be other fixed points, but they'll be smaller than 12. So it's, so that's what we're looking at. But that was assuming that the system size was fixed. Okay? Now, imagine a real-world system that's dynamic. People enter and leave, right? And particularly you're interested in systems where lots of people are coming in. You have a growing peer-to-peer system, right? And you're doing this as, you want people to do jobs for you. This really happens in real systems, right? It's not like I'm making it up. And the system grows. And now you say, well, okay, I'm the system designer. What's my goal? Well, what I've learned from this talk is what I want to keep is the average amount of money per person fixed. So if the right average amount of money was, let's say, 7, so if another 200 people enter the system, I want to pump 1,400 more tokens into the system, right? So I don't want to do what the babysitting co-op did and pump lots of tokens in for no good reason. There's a magic number, but of course, if more people join the co-op, then you want to increase. Now, what's the right way of doing this? Here's system design. Well, so one obvious way of doing this is, okay, every time somebody comes into the system, you give them $7. Why is that not a good idea on the internet? Right, now, you're a system designer, and you want to keep the average amount of money per person fixed at 7. And now your system's growing. You've just had 1,000 people joining the system. This really happens. And you could say, okay, one way to keep the average amount of money, it was $7 before. Make sure each person coming in gets $7. Of course, the average is still going to be 7. Why is that a bad idea? Zombies, 2 accounts. You're all saying the same thing. It's called, right. It's called the civil problem. That's the technical terminology. But it's, I come in, I get my $7. I ask for 7 jobs. Now I'm down to 0. No problem. I leave. My twin brother comes in, gets the $7, and spends the $7 and leaves. But then I also have a triplet. I have another sister out there. She comes in, gets $7, spends it all, and leaves. This is the, zombies, civil problem. Many people are terminal. So that's a very bad idea if you're a system designer. So what do you do instead? Redistribute. So what we suggest is bring people in with 0. How do you raise, so suppose the system doubles in size, right? Before you had 1,000, now you have 2,000 people. You want to bring in a new 1,000 people with $0 because otherwise you're going to get the civil problem, the zombie problem. But you still want to keep the average amount of money at $7 per person. Well, you just give everybody double the amount of money they had before, right? The people who were there before. The new people get 0. So we have inflation here. Yes, but you still keep the average amount of money at $7 per person, and that turns out to be what you want. You want to keep the averages right. Or equivalently, you have the price of a job. Notice that giving everybody twice as much money as they had before effectively is saying the price of a job used to be $1, now it's 50 cents. Yeah. That would be another way of doing it. Then, and again, this would tell you what would be the right price to set it at to solve the zombie problem, right? So you could say it costs $7 to enter the system, and I'm going to give you $7, right? So that would be another way of doing it. It would maintain the average amount of money at 7, but you have no temptation, although it turns out you do, and I'll come back to that, to have zombies, right? Are we together? I mean, this is the kind of thing a systems person has to think about. Samuel. So you got to think about these things as a systems person, and the hope is that the number of people who are entering is relatively small relative to the number of people who are there. So what it means is when you'd enter, you'd have to do some work. Okay, so maybe, now you have to, I'm not denying what you're saying. So you need to think, maybe the right thing to do is charge a small amount to enter. I mean, you can't win here. So if you give everybody $7, then you're going to have a Sybil problem, and otherwise, So we didn't, because we didn't have exponential growth in our simulation. Right. So again, these are things you do. So we didn't do it, and I think as a systems person, you clearly have to do it. So let me just do one or two slides. I know I'm over 7:30, so let me try to finish off quickly. Now, in the real world, as I said, not everybody's rational. Now, these are tokens. There's no happiness value associated to these tokens, right? You don't die happy if you have $1 million stuffed under your mattress, I'm told. But in the real world, there are people who like to have money for the sake of having money. Let me call them hoarders. And there's other people who are altruists who, I love babysitting your kids. You don't have to pay me. Your kids are just so great. I'll do it for free. Let me call those altruists. So, I mean, I think there are many types of irrational behavior. I'm not trying to suggest irrational only in the sense that they're not treating these as just pure tokens, right? I don't want to say necessarily altruists are really irrational, hoarders are really irrational, but they're irrational from, Mark, just give me 1 or 2 more minutes, from the point of view of I know I'm over time, from the point of view of our framework in the system, right? But my guess is that in the real world, you'll find, all sorts of different flavors of irrationality, but a few rather common flavors of irrationality. And I'm suggesting hoarding and altruism are going to be fairly common flavors of irrationality. So it turns out that hoarding has the effect of removing money from the system. So if you understand that 10% of the people in the world are going to be hoarders, well, so what happens now is that critical point just moved over a little bit. You should pump a bit more money into the system, and that turns out to be just right mathematically as well as intuitively. Does that make sense? I mean, they're basically putting the money in your mattress is taking the money out of the system. Well, so you put in a bit more money in the system to compensate. Now, altruists have the opposite effect, sort of, but it's a bit more complicated. Roughly, they're like adding money to the system because they're going to do work for free. Having some altruists in the system makes everybody better off. So if I know there's like 10 people out there who work for free, well, gee, great, because those few times when, with very, very low probability I ran out of money, you're there to babysit for me because you just love my kids and you're willing to do it for free. Great. Social welfare increases, right? You like babysitting my kids, didn't hurt you, and I'm happier, right? So few altruists are good. Grandparents, that's right, they're called grandparents. But too many can hurt social welfare. Let me give you the intuition. I can give you the graph, but so this is what happens. You add altruists to the system, things get better and better, but then there's a crash. Any intuition for the crash? I can give it to you, but does anybody have a sense for, again, real-world phenomenon has a real-world explanation. Why should having, and this actually, in the academic world, I can give you a phenomenon like this if you think there's a lot of people who are willing to referee a paper. Samia, any thoughts? Exactly. So suppose I'm perfectly rational. And I say, hey, why should I work to get a token? There's a bunch of guys out there who are willing to babysit for me for nothing, right? Now, it's not true. So actually, this only makes sense when we assume that, so in our slightly more complicated model, where you don't always volunteer, even if you're an altruist, or even if you need the money. Let's say Friday night, I'd love to volunteer. Sorry, I can't. With some probability beta, I'm busy, and I just can't volunteer. So we've assumed in this paper that beta is 1, that as long as you have less than your threshold amount of money, you'll volunteer for sure. But in our more general result, we assume that there's a certain probability that even if you're an altruist or even if you need the money, you won't volunteer because, hey, you're busy, or you're, in the real world, in the real systems world, right now as it happens, you don't have the spare cycles to do the job, right? It's just a busy time, right? So we assume that with some probability beta, you won't volunteer even if normally you would, right? Well, in that case, imagine there's a bunch of people who are altruists, and I say, why should I volunteer? Because when I want something done, there's a good chance that somebody out there is an altruist and will do it for free. Now, unfortunately, that chance isn't high enough. So there'll be, I mean, it's still not worth it for me to volunteer, but there'll be a bunch of times where I'm going to want something done and I'm not going to, there simply won't be a volunteer. So in a system that's tuned right with no altruists, you can be better off than in a system where there are altruists, because in terms of total social welfare, there'll be times when I'm just unhappy because there's nobody out there volunteering for me. Right? And we can do this by simulation, but that's the intuition. Okay, just about done. Sybils have subtle. So remember, Sybils are these zombies. So you can stop Sybils. You can stop the obvious Sybil attack by saying, okay, you come in with $0. So it looks like you have no incentive to bring in Sybils. Not so fast. You do have an incentive to bring in Sybils, provided that. So suppose you raise your hand. Now suppose I had 5 Sybils. Now, and suppose, okay, I tell all my Sybils, who are just me, right, with different IP addresses or something, okay, I need a job. All of us raise our hands. And of course, if any one of us is chosen, it's like I do the work and I get the token, right? If we can do that, and again, whether or not we can do that depends on features of the system, and I'm not really talking about that. But if we can do that, that means having Sybils, I can arrange it so my probability of getting chosen is higher than it would be without Sybils. Does that make sense? Having a Sybil just doubled my probability of getting chosen, because now there are 2 hands going up instead of 1. Right, so it works if I have Sybils and nobody else does. Now, of course, then we get an arms race. Everybody has Sybils, right? If everybody has another Sybil, I'm, right back where I started, right? So, so there's all sorts of issues here. So it turns out that again, we can show by simulation, and I can't remember if we actually had a theorem about this, that Sybils have diminishing returns. Like even if nobody else is going to have Sybils, 2 Sybils that helps, 3 Sybils helps, but more Sybils helps, but the amount of helps goes down pretty rapidly. So it seems to me in this kind of a situation where you probably do want to charge a little bit to enter the system, even if you're going to come in with 0. But again, this is a systems question, not a theoretical question. A few Sybils can be good. Let me skip this. So we have other results on how to infer the types of agents. What's your alpha? What's your beta? The probability that you'll be able to work even if you want to. So if we have different kinds of agents, unlike this Cockroach equilibrium was homogeneous, it turns out we can infer that, which is something that marketers want to do from the distribution of wealth. We sort of understand how the system's going to evolve over time, so we do have some answers to your question about convergence time. It turns out that in general, multiple equilibria exist, even in threshold strategy, but the one that we looked at was the greatest fixed point that has nice properties. So these are technical results for those interested in them. One thing we looked at is, the last thing, this is the very last thing I want to say, is that we said, well, how hard is it to learn what to do? Right? It's not like somebody tells you, hey, the right threshold to play is 12. Right? You're entering the system. How do you know? Well, it turns out, again, precisely if you don't have this exponential growth, if the amount of growth in the system is relatively small, so you have relatively few new entrants for the amount of people there, you can learn the right thing to do simply by experiment. Right? Because, let me try 10. Let me try 11. Let me try 12. Let me try 15. Fairly little experimentation will get to the right place. This works if most people in the system know what to do, so they're not experimenting. But now if you have a bunch of people entering the system and they're all experimenting at the same time, totally breaks down. You get chaotic behavior. You get really weird stuff. We don't totally understand what's going to happen. So we do provide some theoretical results for learning large anonymous systems. I'm not sure. It depends very, very much on what you assume about how it. I can make it converge if I make enough assumptions. So yes, but I'm not going to try to tell you those assumptions are all reasonable. No, because we're still keeping the price of a job fixed. So the question is it equivalent to an auction market? Right. So let me just stop, and then I'll, so Mark won't feel like I'm abusing everybody's time here. So just to summarize, that it turns out mathematically, it turns out rather amazingly nice. I mean, we certainly didn't expect this. And actually, the way we got here is I had Ian, who was my student at the time, do simulations. Simulations was saying, there really is a nice best pi function. There really is an equilibrium. And it felt like there must be something going on mathematically. And I had done other work where I used maximum entropy, and somehow I sort of stared out for a while. I said, this sort of feels like the other work. Ian, go think about it. That's why we have students. And it turned out magic maximum entropy worked. So I don't want to say that, boy, we were so brilliant, we knew all this stuff was going to happen. We really did it, and I'm a theoretician. I usually start by proving theorems. This is probably the first paper in my life where I started by telling a student to do simulations, because I don't really have a good sense of what's going to happen. The simulation showed we were getting really rapid convergence with about 100 agents, and it looked like there was a nice equilibrium in threshold strategies. And we said, God, this is happening every time. There must be some theorem here that explains what's going on. So then we proved the theorem, but you know, it didn't. So I told the story not the way it happened. Of course, now that I'm giving the talk, I tell you about the theorem and I explain it, but that's not how it happened. So for a theoretician, it's sort of nice that you can totally characterize what's going on in the system for a fixed number of agents using maximum entropy and using the monotonicity of best apply functions. That's the technical meat of the paper here, but if you don't follow that, don't worry about it. For the system designer, the message here is the right quantity to manage. The only quantity you care about is the average amount of money per person. And more money is better up to a point, but that point is a critical point. There's a cliff there, and you might want to trade off efficiency for some robustness. You want to back off from the cliff just a teeny bit. We can sort of understand how to deal with sort of standard, if you like, standard irrational behavior like hoarders and altruists and with civils, but I think there's a lot more to be done. And one of the things that I think I would really like to do, so let me just close with this, is understand the impact of auctions. So people are asking at the beginning, you know, shouldn't you have auctions? And my intuition says it depends on the kind of market. If you have a market with many buyers and sellers, auctions won't buy you much. Whereas if you have rather small, specialized markets, auctions are the right thing to do. Now, that's an intuition. The mathematician in me wants to formalize that, but let me just give you the intuition. I can go to the large grocery store near my house, which is a Tops or a Wegmans, and even at 10 o'clock at night, now it happens, Wegmans is open 24 hours a day, but even imagine a store that closes at midnight, and I can see there's a lot of tomatoes left. And I know that by tomorrow they're going to go bad. They do not auction tomatoes. There's a fixed price for tomatoes. Now, okay, I know I can also go to the souk in Egypt or you know, in Jerusalem, and there you can bargain for vegetables, right? I mean, but certainly in large grocery stores you can't. And they've decided it's not worth it. Now, there's lots of reasons. There's overhead in allowing auctions, right? You don't have them in large grocery stores. You do have them in more personal, smaller settings like markets. So I think there's a technical question here, assuming you're a system designer. There's real overhead in building a system with okay, I know Google does it, so you know it's the wrong place to be saying this, but certainly in some kinds of markets, instituting an auction, there's real overhead. And it's much simpler, and definitely producers and consumers like the certainty of fixed prices. I can plan a whole lot better if I know this is going to cost $5 for the next year. I mean, I can figure out what my expenses are going to be. I don't like, I mean, my intuition is with very large markets, with a large number of buyers and sellers, you didn't have to have an auction because you're going to end up at a certain fixed price anyway. Things aren't going to change much. Again, assuming everything's stable. Things change if you have all of a sudden, explosive growth in the number of players. Then you get inflation, right? And we can see these phenomena. Yeah. Okay, so they do. So mind that. So again, I'm not saying it's silly. It's not that common though. So I'm definitely, you should not take what I'm saying as auctions bad, fixed price is good. I am saying that fixed auctions incur some overhead, and you have to think hard about when to do them. They don't have them all the time. I assume they do it at the very end of the day. Well, maybe so, but these were yuppies. They didn't want to get into, I mean, again, think about the sociological context. You don't want it to be the case. So it's not like I'm going out to the workforce and posting an ad on the internet. This is a group of 30 people where they all know each other. They're not going to bargain about the price of babysitting. I mean, maybe they should. Okay, so there's some interesting. Yeah, they're obvious. So Mark, it's 12 minutes to 8. I mean, I don't mind cutting it. You can come to me and ask me questions. I'm here. A couple more questions, and then maybe we'll. Absolutely, it's a cultural phenomenon. Believe me, I know. I don't know what it's like in the face, and they like to tell tourists this is my face. Oh, I've been to, well, not Tehran, but many other countries, and my daughter calls me in to bargain for her when she wants to do some shopping in the Jerusalem market, and because she says I'm a better bargainer than she is. But they like to pretend the prices are fixed. They certainly won't slug you in the face if you take their first offer. They're very happy to. Well, they might think you're a fool, but right. Well, depends. But yeah, it's definitely a cultural phenomenon. There are many issues here. I'm not trying to say there aren't, but again, even so, but I think there's more to it than just a cultural effect. I think there are markets where it's much simpler. As I say, for a producer, there's a comfort knowing a fixed price. So there's some real benefits. So this is the interesting. I talk a lot to economists. So I think you can say you leave money on the table if you don't have auctions. It's more efficient to have auctions. In some settings, I believe it's true. And the question is, what's the cost of inefficiency? I mean, I have the paper title written. You know, the paper is going to be called The Cost of Inefficiency. So yeah, there's how much time and your assistant designer, it's more complicated. I mean, I think there are many, many issues. So 2 more questions. To take a random stock. Right. Sure. That's one, again, it depends very much on the setting. That's an instance of where you might argue that there's a price to be paid for the efficiency of auctions. And so my own feeling is I would love, as a theoretician, to be able to characterize the features of markets that make fixed prices the way to go, right? And you sort of give me one instance, and my gut tells me as a theoretician that there ought to be a theorem here that sort of characterizes them, but future work. Okay, well, 20 questions when there's room for one. Right. That's a great question. I mean, my results have nothing to say about it, right? We were assuming there's only one market. There's a fixed price. You can't go elsewhere to get your job done. Now, you're talking about a situation where there's several markets, right? So that if you don't like my $1 price, you can go somewhere else and get it for 75 cents, right? That introduces a whole bunch of complicating factors. I'm sure all my results go away. So as a technical matter, I have nothing to say about it, but it's certainly an interesting question. But again, why doesn't everybody go there? So you have to assume that as an economist, you have to understand what are the features of the various markets. I mean, if all markets are the same, then in the end, there'll be one market because, if the discount market is in every way as good as the non-discount market, then why would you ever shop at the non-discount market except for maybe if you don't realize the discount market is there? So it's not found rationality, but lack of information. So Mark says that was the last question, but I'm willing to stick around if you have more questions.
Thank you all very much.